All right, the light is on. So what we need to do, we need to finish a little bit the discussion on model selection and model comparison. So if you remember, everything we have to compare models is the marginal likelihood. And I gave you sort of a general framework, which is this little equation on how to compute analytically the marginal likelihood. Okay? So just as a summary, if you take Bayes' rule and the posterior for the parameters, likelihood priors, and this is what we want to compute, effectively, if you write things in a normalized terms and normalization factors, it comes that the model evidence for a given model is nothing else but the normalization factor of the posterior divided by the normalization factor of the prior divided by the normalization factor of the likelihood. This is very powerful, and obviously for different problems when you plugged in things there, things will look complicated, okay? But for many problems we can do this analytically. What the difficulty, of course, will be when you try to optimize, when you try to select different parameters and you try, let's say, to maximize the evidence, and you have to do some optimization on whatever comes there. That can be a little bit complicated to do by hand, so you have to use numerical approximations. All right, so what I want to do is today, I want to continue for a while on computing the evidence and sort of defining some Bayesian criteria that will allow us to compare models based on the maximization of this evidence. So what I'm going to do is, okay, so yes. So what I'm going to do is, I'm going to start with a very general approximation for the posterior of the parameters. And that approximation goes with the name Laplace Approximation. If you have not seen it, I discussed this extensively in other classes, so I'm going to try to explain it for those who have not seen this before. So if you have a lot of data, in a natural setting, the posterior peaks basically becomes like a delta function, or even better, it becomes like a Gaussian around the mode of the distribution. Okay, that's what the idea is. So the more data, the more Gaussian looks like, and you know, the Gaussian becomes narrower because you become more certain about your predictions. So the idea of the Laplace approximation is to fit a Gaussian on the top of your posterior, where that Gaussian is basically centered on the map estimate, on the maximum of the posterior, and has the same curvature as the actual distribution at that point. So if you want to see the algebra, think of a Taylor series expansion of the log posterior, where you keep only up to second order terms. So if you know, I'm going to tell you how this is coming, right? But think of this if you take logs, think of a log approximation of the log posterior, so you will get a constant term. We don't really care right now, a constant term. You will get a linear term, which will be involving the derivatives of the log posterior at the map estimate. And how much is that derivative? By definition, what's the derivative of the posterior at the map point? 0. And the only thing you're left is basically the quadratic term. That's a Gaussian. All right? So a Gaussian approximation to the posterior looks, this comes from the constant term. It's obviously, you need to normalize the Gaussian. It is centered around the map estimate. And A is minus the second derivative of the log posterior computed at the map estimate. All right? This is extremely powerful, right? Every time you have difficulty to do anything, what you do is you do a Laplace approximation hoping for the best. Okay? It's very universal. And obviously the only thing it assumes is that you have data. If you don't have data, it will be very questionable to use this approximation. Also, if your posterior is multimodal, you cannot use it. This is approximated with a single mode Gaussian. All right, so what I'm going to do is I'm going to try to go back to the model evidence and give you an approximation, and then define some basic criteria for model selection, where we use the Laplace approximation for the posterior of the parameters. Okay? So let's see where this is going to take us. So what I have here is, don't bother about the conditioning on model M, all right? So everything is conditional on model M. Consider that we work for a very specific model, and for that very specific model, the marginal likelihood is the likelihood that you see here times the prior divided by the posterior. I rearrange the terms, right? Usually you see the posterior is the likelihood times the prior divided by the marginal likelihood. So I put this is what we want to compute. So let's do the following thing. We're going to take logs of this, and we're going to estimate all the terms around the map estimate of the parameters. So we're going to approximate this equation around the map estimate. So the log of this is the log of that, and the log of that minus the log of this. And this will be approximated here by what? The log, what is this? The Laplace approximation, all right? Okay, so this is the Laplace approximation, all right? What did I do? I said I'm going to approximate everything for theta equal to theta map. So what is going to happen to this term? It's going to disappear. So what I'm getting is the log likelihood, the log prior, this d over 2 log of 2 pi, okay? D is the dimensionality of the problem minus this log of the determinant of A, and I remind you A is minus the second derivative of the log likelihood computed at theta map. All right, so effectively what you see here, it is a very nice approximation of the model evidence, all right? So it, here what it says is, okay, you have the log of the likelihood computed at the map estimate, you have the log of the prior, okay? So everything is computable, but we can simplify. So for example, here it says you have the log of the likelihood computed at the map estimate. Maybe we can use the MLE estimate there instead. All right? So that's what, I mean, the two estimates, of course, when you have lots of data, will converge to the same answer. But somehow, maybe, you know, everything here is computable. So let's see what I'm rewriting the same equation, and I'm going to take an approximation of this equation when the number of data in the problem goes to infinity. All right? So here we're going to make an assumption that you maybe have seen. It comes in other scenarios also in machine learning. I remind you that this matrix A is the second derivative of the log likelihood. And what happens to the likelihood as the number of data points increases? Increases. Okay? So we're going to assume that A is really n, or proportional basically to n times some constant matrix. Okay? So the log of A, of the determinant of A, is the log of the determinant of n times A0. This will give you log of n to the power d times the determinant of A0. And because this is constant, and we're interested for n goes to infinity, this log of the determinant of A is d times log of n. Very nice simplification, okay? Again, d is the dimensionality in the problem, n is the number of points, and because I'm going to take n going to infinity, the log prior, who cares, right? It's a constant term, so we're not going to bother. So the log of the evidence of the model M is this log likelihood minus, this is very important now, here I had log of A 1/2, so 1/2 times d log of n. And what you see there, it is basically what is called the Bayesian information criterion. So in a few lines, we define something very powerful, all right? So a lot of times you're going to say, oh, select the model that maximizes this right-hand side that you see there. And as I said, often, instead of this map estimate, they use the MLE estimate, but you will see saying, oh, the best model that maximizes is the model that maximizes that. And you notice again the interplay here of two terms, one that says, yes, maximize the likelihood, but the other one penalize the complexity of the model. So that's the Occam-Razor's problem. You know, the simpler model that does the job basically is the one that maximizes those two terms. But what is nice is that this criterion really has a Bayesian setting because it is an approximation to the log evidence of the model. So it doesn't come out of nowhere, it is really an approximation of the log evidence. All right. As I said, there you can put different things. So this was the dimensionality D, which is the number of parameters in the problem. If you want, you can put the MLE estimate, okay? But what is important that I want you to remember that here you have minus D over 2 times log of n, because some non-Bayesian models, they have something else there. I don't know if this is going to show up in the next slide. Yes. So this is a non-Bayesian criterion, the Akaike information criterion. And you notice here it says minus D, the degrees of freedom basically in the model, there is no n. So the penalization for complexity is way less here because there's no n. Not only that, this criterion, it is not an approximation to the marginal likelihood. So really, it's heuristic, right? You cannot, you say, I want to maximize the log likelihood and some penalty. Yeah, fine, but that penalty does not come in any Bayesian setting. This model, it is an approximation to the log likelihood, and this is the most rigorous thing that you should use in your calculations. This slide, it may be a little bit ahead because we have not done anything about regression yet, but since I'm assuming 50% of the class has seen this in other courses, certainly we covered this in the fall, I have an application basically of this Bayesian information criterion in the context of regression. So remember, in regression, what you do is I give you points xi, I give you points yi. You try to fit some linear model that looks like y equal w transpose x plus some Gaussian noise. And the MLE estimate is of the parameters is the least square solution that you see here. The MLE estimate for the noise is basically the variance defined by the observations and the predictions of the model. So this is the empirical variance. All right. So if you plug in everything, if you calculate the log likelihood, and you use this expression and the penalty, effectively what you get is this nice quantity here. Okay. So the Bayesian information criterion looks like that. So if you have this and you say, what is the order of how many parameters should I use? Well, it's basically everything has to do with the optimization of big. Okay, so some of the plots that I show you that contain, you know, I was showing to you the posterior of each model, which was sort of proportional to the marginal likelihood. Those type of plots are sort of equivalent doing calculations, plotting this big, because the big is an approximation of this marginal likelihood. All right, so we're done with this lecture, and so we're gonna be moving to something else now. So what we're going to do is we're going to discuss a little bit about prior models and a little bit about the concept of hierarchical Bayesian models. And I think at least one of your homework problems is very much related to this lecture, so it's an extremely important topic. So hopefully we can cover as much as possible today, the rest tomorrow. So the first part is going to be very basic because I'm going to remind you things that you already know about prior models, but it's better to sort of summarize these things, not assuming that everybody has seen them before. All right. I don't have to tell you very much about prior, but there is no such a thing as what is the best prior for the model. All right? It's very subjective. Whatever works for you, it may not work for somebody else. The only thing I am going to say, if you have some prior knowledge, either based on data or any other means, you should introduce that knowledge in the prior. You should not feel ashamed from having something that is very subjective. The idea here is Bayesian setting is subjective, so whatever you think is appropriate, you need to introduce it. Somebody will disagree, but that's what this Bayesian formula is all about. So we're going to discuss some sense of informative priors that contain some information, and then if you don't like that, we will discuss about non-informative priors and give you a summary of what is out there that maybe you can use. On the informative priors, we already have seen conjugate priors, right? And a lot of these conjugate priors go with what's called the exponential family. So I'm going to review a little bit what the exponential family is. And in that context of the exponential family also fits this general theme of maximum entropy priors. And implicitly, all of these things are together, but I will not elaborate in all of these categories basically separately. All right, so let me define, I'm going to put everything up. So let me define what's a conjugate prior. So we have a likelihood, you assume a prior. So we call this prior to be basically conjugate to the likelihood when the posterior comes to be of the same class as the prior. Okay? So you have a prior from some class of priors, all right? You multiply with the likelihood, then it comes out that the posterior looks exactly like the prior, but with updated parameters. So we call that the family of the priors to be conjugate to the family of the likelihoods that we play with. And some examples that we have seen before. This is the coin flipping experiment. If, let's say, you flip a coin and the probability of heads is theta, and nh times you get heads, n minus nh you get tails. Obviously, the prior that is conjugate is a beta prior. So if you multiply with the beta prior, effectively the posterior looks exactly like a beta prior. The only difference is you have updated the counts from alpha and beta to alpha plus an h and beta plus n minus an h. Okay, so in some sense, these conjugate priors are mathematically convenient, and maybe for the wrong reason, people are using them because the algebra looks simple. And not only that, but you can see sort of, you can even assign sort of pseudo-physical meaning to the prior coefficients a and b, because sort of, if nh and n minus nh is the number of heads and tails, you can call a and b the number of, the equivalent number of heads and tails before you collected any data. They are the pseudo counts, if you like, so effectively you update the counts by summing the pseudo counts and the real counts from your experiment. So let me generalize. If you have not seen this topic, I would recommend that you read more. Maybe you go on my slides from the fall or last year to read more about the exponential family. So we need to generalize and define what's called the exponential family of distributions. And it looks like that. This is the definition. Okay? So theta are the parameters in the model. So there's some function of theta, some function of the data x. And then there is, this is the important term. That's why we call this exponential. There is exponential of r of theta, which is a vector, dotted with t of x, which is in general a vector. It's a function of x, a vector function of x. And we call t of x the sufficient statistics of the problem. So effectively here is, when it comes to estimating theta, The only thing you need to know about the data x is this function t of x, because that's the only thing that comes in that expression. And that's why we call this the sufficient statistics. Okay? And I will give you specific examples in the following slide. If it happens that this is simplified the way that you see here, we call this the natural family of dimensionality k, where k is the dimensionality of x, and obviously the dimensionality of theta. These distributions are extremely powerful, all right, and they come everywhere, and in many ways their origin is in the statistical mechanics, and that's from where people in machine learning extrapolated and came up with this generalization that you see here. So let me give you some examples. You see on the top the normal Gaussian distribution, variance equal to 1. So the only unknown parameter here is the mean. So you can actually write it in the natural exponential form with these substitutions as you see here. All right? So you're going to get e to the minus x squared over 2. All right? So that will define the function h of x. There is inside a minus theta squared over 2 that will define psi of theta. And then there is 2 times x times theta. So the sufficient statistics here is just x. Okay? And r of theta is equal to theta. If both the mean and the variance are unknowns, basically you will have to introduce some vectors, put it on the first form, and you see the equations here. Okay? And so the equations look like that. Now, I am going to, if we have time, I'm going to spend at least one lecture on generalizing many of the concepts of this course for the exponential family. The only thing I'm going to tell you right now is you just need to keep in mind that most of the distributions that you read in books are written in terms of moments, right, like the mean and the variance, but the parameterization implied here, it may be way more natural in other settings. Not everything in terms of moments is the best way to go, okay? So you can see obviously here, when you look at the Gaussian, you say, wait a second, this is very complicated. What are you telling us? This is nice, because you are seeing this for a million times, right? This is not nice. Well, you know, once you have it in this form, and lots of other things are very nice. In particular, what's going to be very nice is that you will be able to make calculations for all the distributions and provide one form that fits many, many different things together. So you're not going to only work with Gaussian, but all the family of, in the exponential family of distributions, and so you'll be able to generalize in one page and do, let's say, regression or classification using this sort of distributions. All right, now why do we care in the context of priors about the exponential family? So let's say that the likelihood looks like this. All right? So obviously exponential family. So what I'm going to do is I'm going to use another prior that's also from the exponential family. All right? So this is the prior of theta. And I'm going to write it, because it has to be conjugate, like this. Does this to you look exponential? Does this look, do they look conjugate to each other? In other ways, if my prior is like that, will the posterior have a similar form? Multiply them and see what happens. Well, if you multiply them, what you will get is, you will get r of theta times mu plus t of x, all right, minus lambda plus 1 psi of theta, okay? So it is exactly the same form as the prior. The only thing that has changed is you went from parameters mu and lambda of the prior to mu plus the sufficient statistics of x, all right? And instead of lambda, you go to lambda plus 1, okay? So obviously, you know, immediately we can see the usefulness of conjugate priors in the context of the exponential family distributions. So the posterior here is nothing else but really the prior with these updated parameters that you see here. Let me just write these formulas because I will use them on some examples in the lecture today. Again, I strongly advise you that you read at least either from Bishop's book, one of the chapters, or I think it's chapter 2 from Murphy's book on the Gaussian distribution. But if you think you have a likelihood that's Gaussian, and I take the variance to be constant, and I only collect one data point, so my likelihood looks like this. The conjugate prior to for the mean is a Gaussian, all right, with mean and variance mu0 sigma 0 square. So the posterior, so the Gaussian is in the exponential family, right? So when I multiply this with another Gaussian, I get a Gaussian. So the posterior is also in the exponential family. And it comes out that the posterior mean looks like this. And the posterior variance is updated like this. If you like, actually, the inverse of the variance, which is the precision, the posterior precision is the prior precision plus the precision of the noise in the model. And the posterior mean, it's really a weighted average of the prior mean and of the data point x1. Okay? So these are generic formulas, right, for the Gaussian. Okay? The bottom line is here. This is conjugate to that. They are all in the exponential family. So the update of gives you a posterior, and the posterior, the only thing you have to do is update mu0 and sigma 0 squared to the values that you see here. Of course, you can do this a little bit, push it a little bit further. The posterior predicted distribution is also in the exponential family, it's a Gaussian. So if you collect the data x1 and you say, what's the probability that I would see on my next experiment x? It comes out that the distribution is also Gaussian with mean, the posterior mean, and variance, the noise variance sigma squared, and the variance of the posterior that you see here. Again, I don't want you to remember any of these formulas, all right? But I'm just telling you that this thing somehow, this update in the parameters of the prior are the result of the fact that these distributions are all conjugate distributions coming from the exponential family. You can generalize this for the Gaussian to many measurements. So if you go and you collect, let's say, measurements x1, x2, xm, okay? And I keep, again, I suppose, sigma squared constant. So my only parameter is the mean, and you put a Gaussian prior on the mean. The posterior still comes, obviously, to be a Gaussian, and I only give you the results here, all right? So the results comes. They have a very nice interpretation, actually, when you looked, when you work on the slide and you play with the details, you will see two things. If you define n0 to be sigma 0 over sigma squared over sigma 0 squared, this is the noise in the model, this is the variance in the prior, all right? Somehow the interpretation of n0 is that there are n0 virtual observations induced by the prior. Why is that? Because look at that. When you compute the variance of the posterior, it comes to be sigma squared divided by how many data points you had plus n0. So it makes sense to interpret n0 because the effect of the prior as the prior virtual dummy observations that you have. And similarly for the mean, look at this. These are all the data, all right? And then you have n0 prior observations at what strength? The strength of the mean of the prior. Okay? I mean, again, the results come in a little bit different form, but if you introduce this concept of virtual observations, you can see to go from the prior to the posterior, the only thing you need to do is update these, where is my prior model, update mu0 and sigma 0 squared to sigma n squared and mu n. By the way, I noticed yesterday when, as I told you, I use Wikipedia all the time. So when you click conjugate priors, you come with a beautiful long table, all right, that has everything with all of these results ready for you to use. It gives you the prior, the likelihood, and then it says, here's the posterior mean, the posterior variance, and gives you even the predicted distributions in closed form. Okay? So no excuses, oh, I have no idea what this is there. Okay? It's there, and I use it, and you should use it as well. And so here is a little table, not as comprehensive as the one Wikipedia has, but what you see here is likelihoods. These are the conjugate priors, and the posteriors that you see here, it's nothing else, but immediately you can appreciate, right? What you do is you update the parameters of the prior. I mean, I see here if the precision is the unknown variable here, 1 over the variance, and you put a gamma distribution as a prior, that's standard. The only thing you have to do is when you compute the posterior of the precision, instead of alpha and beta, update the parameters the way you see here. Okay? So, and again, this is for one data point, you know, and I believe the table in Wikipedia gives you for many data points as well. So instead of x's, you have the sufficient statistics of x that come in the picture. All right. So I'm going to do one example right now, and I wish actually we had this as a homework problem, but you know, there's always room for another homework, right? So what I'm going to do is I am going to try to convey that if you are not very happy using a conjugate prior because you think it's okay, mathematically elegant, but somehow you don't feel it's the right prior, what you can do is you can actually use a mixture of conjugate priors. So for example, in the coin problem, you know, if let's say that the probability of the number of heads, theta, is the unknown, right? You can say, well, if my coin is fair, this is a good prior. But you know, if the coin is not fair, this is a better prior. Well, that's fine. If you don't know if the coin is fair or unfair, how about if you use a mixture of the two priors? And it comes out, and I'm going to show you the derivation on the next slide, that if you have two priors that they are conjugate to your likelihood, the mixture of the two priors is also conjugate. Not only that, it comes out that the posterior, it is basically a mixture of the posteriors of these distributions that you see there. So basically, these two priors get updated parameters, and the coefficients become posterior mixing coefficients. Right? So this is sort of the prior mixing coefficients, but now once you collect data, the data will point more, let's say, to a fair coin than an unfair coin. So you're going to have posterior mixing coefficients. All right, so one slide contains the truth and everything you need to know, but one slide can be, it's a comprehensive slide. So, so what you see on the top is a mixture of k priors. All right, so this is what we started before. So each of these priors, we assume they're conjugate to your likelihood, but now we form a mixture, and these are the prior mixing coefficients. Okay, before you see any data, you say, put more weight on a fair prior, less on unfair, but you know, here I have k priors. And what have I done here? And I put this in an equivalent form. Can you tell me what is z? I introduce always a new variable, z. So what is z? How do you, if you have a mixture of two distributions, how do you sample from a mixture of two distributions? I mean, if you had a mixture of two Gaussians, how do you sample from a mixture of two distributions? So you decide which one, right? And then you sample from that one. So what is z? So which prior to select, all right? So, and this is effectively, it's an indicator variable, right? That tells you if you sample from this prior 1 or prior 2, etc. But this is the prior that you put on z equal to I before you see any data. So really, wi, you can think of this as some prior mixing probabilities, right? Some prior mixing probabilities. Okay. So let's plug in this on Bayes' rule, all right, and see how the posterior will look like. I remind you what's the posterior is the prior, which is, you see here, times the likelihood. And then I have the normalization factor. I have, I'm going to have to integrate this thing in the space theta, okay? So, and I put a different index so I don't confuse you with the I there and the J, all right? So what you have here is a normalization factor for the numerator, and I call this normalization factor to get it out of the way. I call it A, okay? It's just a normalization factor. So the posterior looks like Wi over A times pi I of theta times the likelihood. So what I'm going to do is I am going to divide this whole thing there. I'm going to divide it by this integral. What is that integral? What is that integral? Remember here, right, inside this summation, this term alone is a prior I times the likelihood, right? Priors I times the likelihood, and this is what? The normalization factor of that unnormalized posterior for component I of the prior, okay? So obviously if I divide by this, I'm going to have to multiply this whole thing there by this integral, right? I cannot just divide by the normalization factor. That's why you see Wi prime, because now Wi prime is, it is Wi divided by A, this is A, times that normalization factor that you saw. Okay? All right? So, will you agree with me that this is the posterior pi I of theta given the data? These two terms together, that fraction there? Yeah. So what do you have? Literally, what you have is, these are the posterior mixing coefficients, and I'm writing them explicitly like that. And these are the posteriors where each term you're using a different of the prior components. You see that? So suddenly, the posterior, it is a mixture of posterior distributions, all right? All of them are basically this pi that you see here. It's an update of this prior pi I of theta. And this coefficient here is just the definition. Basically, you see it on this last equation. And if you want to be adventurous, and I added this, I think, yesterday or so, you can actually write this thing a little bit nicer than the way I have it here. You can use Bayes' rule for the posterior of the mixing coefficients given the data. So what I have done is, this posterior of the mixing coefficient I is the prior, times the likelihood, if your prior was prior I, divided by the normalization factor. And if you explicitly plug in all the information, what is this P of Z equal to I? Is Wi, remember? That's the prior mixing coefficient. What is P of D given Z equal to I? That's the marginal likelihood for when you use model I. That's that. And that's a normalization factor. So basically, if you want to see the proof this way, or you want to see it with a this, you get the same answer. The bottom line is the posterior, it's also a mixture of distributions, and each of these distributions is basically an update of the prior, because especially, I mean, in the particular case that these priors are conjugate to the likelihood. So if you have a mixture of priors where each component is conjugate to the likelihood, then the mixture is also conjugate to the likelihood, and this is the proof. The posterior comes to be basically a mixture with distributions that have the same form as the prior, but with updated values. You should do a simple example on this, all right, I advise you. And in particular, you should reproduce all the results on the slide and tell me if they're right or wrong. Okay? Because you can look at the slide for as long as you would like. If you don't do it by hand, you don't understand what's going on. All right? You have to do it. And if you do it, you may come up and say, you know what, your numbers are not right, which is possible. So what's the problem? We had the toss of the coin, so we use two priors, let's say a fair prior and an unfair, so the mixed coefficients 50-50. We took the coefficients given, okay? We do now some experiment, we get n1 heads and 0 tails. So the posterior will be these posterior mixing coefficients, and then the priors will be updated exactly the way we do when we only have each prior alone. So the coefficients A1 and B1 will be updated to A1 plus N1, B1 plus N0. So this is very easy to do, right? Because we did this on a previous slide. The complication now is, how do you compute this posterior mixing coefficients? And the idea is Bayes' rule. So the P of z equal to k given the data is the prior mixing coefficient, which is 0.5. And what is again P of d given z equal to k? That's the marginal likelihood when you use prior k. And do we know what the marginal likelihood is for this model? You remember I gave you analytical formulas in terms of the normalization terms? You remember? That's the analytical formula, for example, when it's equal to 1. Remind me, what normalization term is this? It's the normalization term of what? Of the prior. 1 over this is the normalization term of? Remember, in my likelihood, in n experiments, I got n1 here. So this is the normalization factor from likelihood. And what is the whole thing on the numerator? The normalization of the posterior. So basically, these terms here for each prior separately can be written explicitly. So we know the coefficients, we know this. And here's a wonderful result, right? So the mixture of the two priors is this red curve. And the posterior basically is also a mixture of two distributions. And it doesn't look as intense as the prior because now you collect data. And actually, if you collect even more data, this will become unimodal, I'm guessing, right? I mean, it will look like that, you know, that the coin is fair, basically, with lots of data, or unfair. So you will converge more or less to one mode. But this distribution, as you see here, it's a mixture, and it is what you see. Okay? Again, I strongly advise you to, the actually posterior, it's written explicitly here, to check it up, okay? If you want, I mean, you can write actually a little computer program, and if you don't want to write a little computer program, spend 2 minutes, click that, and look at the 10 lines MATLAB program, and convey to yourselves that it's all algebra, but you know, if you understand the concept, algebra is not very important. All right, so I like this example, even though it is for biologists, okay? So let me try to explain this in a sort of non-biological terms, okay? So consider that we have a sequence, okay? This is a biosequence analysis. So we have different locations in the genome. And in some of the locations, I'm not going to give you any details here, but let's say we have 4 different possibilities of happening. And these 4 different possibilities are represented with the letters A, T, C, and G. So in some of the locations, we may have 1A, 1T, 1C, 1G. In some other locations, we may have everything G. So this big letter indicates that the only thing happening on location 7 is this capital letter G. So this looks like a multinomial type of distribution because at each location there is a probability of having an A, a probability of having a T, a probability of having a C, a G, etc. So the distribution. So if Z defines the location in the genome that I am looking, and NT is the counts of each letter in that location, this is a multinomial distribution. Okay. So the objective here is to compute the, if you like, to make a plot of a diagram that looks like that, and using data to tell me how many, in what locations I have, what's the probability of actually having an A or a T or a C or a G on a given location. The reason I like this example, okay, is that the distribution we want to compute is conditional on this variable Z, and this variable Z tells me if this location is going, I'm going to have all G's or all A's, or I'm going to have one A, one G, one T. This is what's called if the location is conserved or not, okay? So why am I telling you about this? So obviously there are 4 letters here, right? So you have to use a multi-nully distribution to describe this. But I wanted to tell you that somehow to produce this distribution, you're going to have to compute this integral, all right? We don't know what the probability of having an A or a G or a C is. So this diagram that you see here is an integral over the parameter space for a given location Z, okay? Of the likelihood times the prior with all the parameters integrated out. So I want to only tell you about this little thing on the bottom, okay? Suppose that I give you that in one location, we know that Z equal to 1. So we know that in that location, I am going to have either all A's or all C's or G's or T's because that location is conserved. So basically, we need to have a prior that tells me, you know what? I cannot get a little bit of A and a little bit of C and a little bit of G and a T in that location. Either everything is going to be a big G or a big A or whatever other letters I have. And the prior to do this is a mixture of Dirichlet priors that you see here, where each of the mixture components basically has a probability mass in one of the edges. Here it is. It's a 4-dimensional problem. I plot this only in 3D here. But basically, if you look at this particular distribution, right, it puts all its mass here, and only the event in this quarter is going to happen. The rest is 0. Okay? So what we need is we need a mixture that looks like this, that says either I'm going to have an all A's, or let's say the second letter is going to be all C's, or in this case, all T's. Okay? So if you do this, you can actually get an analytical formula. You can do this integration exactly, and you can plot a diagram like this for the genome sequence. And sort of this is a very nice, again, application of a mixture of conjugate priors, in this case, to this multi-nully distribution. You can come up in your own problem, right, with different scenarios. If this is very confusing, basically, this slide summarizes everything you want to know, at least in a fundamental way. But here we use a mixture of 2 beta distributions. But actually, you can go further, and you can use a mixture of Dirichlet distributions that where each of them uses prior knowledge. In this case, the prior knowledge comes from this conditioning that in that location, only one of those 4 letters is conserved. There is dynamics to this problem, by the way, because if one location is conserved in let's say, location 7, there is a higher chance that the neighborhood location will also be conserved. And the way you do this is by using a Markovian model for ZT. And maybe that's another course, another time. Okay? All right. So summary of the conjugate priors. They are sort of the least informative priors you can use. You can put some interpretation in terms of imaginary prior observations. You cannot really use them for all likelihood models. So if your likelihood is a computer code, there is no hope that you can use these conjugate priors. Even this idea that I showed you with mixture of priors, of conjugate priors, that's a very difficult thing to do in complex models, so it will not work. And if you have constraints on the parameters, like if you say if the parameter, let's say one is a variance, and you say the variance has better be positive, you cannot enforce these constraints with conjugate priors. Okay? So there's pros and cons basically that you need to consider when you do these things. So what we need to do is we need to discuss about non-informative priors, okay, and see what's going on. So I remind you the towing cost problem, and I think this was in lecture 2, all right? So we had the Bernoulli parameter, right? The probability, let's say, of having heads or tails, and we use at the time I told you the most non-informative prior is a beta 1, 1, which is a uniform distribution. You remember beta is theta to alpha minus 1, 1 minus theta to beta minus 1. So when you have 1, 1, that's a non-informative. But you remember when you take the posterior mean, it comes out actually that the distribution, it's an informative, but not really an informative, because in the posterior mean, you edit 1 and 2 in the numerator and the denominator. You remember the plug-in approximation for the posterior mean, the add 1? So even though it seems the prior that should not be doing anything at all to the problem, and the likelihood should decide everything, I remind you, all right, that when we computed the posterior mean, there was the add 1 effect, okay, which means that the uninformative prior was not really an informative, right? So the definition, you think it's a uniform distribution, you don't say anything particular, say can be anything. Well, yeah, if you don't say anything, why is this changing? Okay? So I will show you later on that the really uninformative beta prior, it is not the beta 1, 1, it's the beta 1/2, 1/2. Okay? And I'm going to derive this one with, in a few slides. So the really uninformative prior is the beta 1/2, 1/2. Okay? So one thing you need to be concerned when you use uninformative priors, right? You need to be worrying about the parameterization of these prior distributions. And so, if you go and assume, let's say that prior on some parameter lambda is uniform, if you go and change the parameterization, and from lambda you go to a parameter eta, the distribution on eta is not anymore uniform. So when you assume in your problem, say I'm going to use a uniform distribution, be sure you really know what parameterization you use, because as you change parameters to do calculations, something that looks uniform in lambda, when you work in eta, you realize that it's not uniform. So here is what I told you on the lecture on Tuesday. When you change variables, what is conserved is the probability mass, P of eta d eta equal P of lambda d lambda. And because P of lambda here is uniform, basically the distribution in eta, it's not uniform, it's proportional to eta. Okay? So we need to be sure basically that this reparameterization effect is accounted properly when we work with non-informative priors. So let me give you a few examples of non-informative priors for the mean and the variance that is going to be very handy basically for doing Bayesian analysis. So first thing I want to do is, let me put all of this up. I want to define what is called a translation invariant prior. Okay? So a translation invariant prior is a prior that has this form. Okay? And where mu is a parameter, okay, it's a location parameter. And why do I call this particular thing translation invariant prior? Because you can solve the following thing. If you shift x to x plus c, all right, and you try to compute the probability density for x bar, then it comes that the probability of x bar actually has the same form as the probability of x, with mu bar now equal to mu plus c. How do you come up with this? basically what you need to do is use this transformation, plug in the transformation of coordinates, and in half a line, you will come up basically that this distribution looks like this. Okay? So we call this translation invariant prior. And the idea here is, if you think of the mean being, let's say, mu to be the mean of the distribution, the idea here is, if you take this distribution and you shift it by some amount c, you want to be sure that if you look at a certain interval under the distribution, that the probability mass is conserved. It does not change as you move the distribution. So effectively what you need to do is, you need to be sure this derivation basically is exactly what is contained in this formula with the transformation of distributions, but is given in sort of down-to-earth type of calculations. So the idea here is, for a translation invariant prior, you want, if you take the probability mass when you integrate from A to B, you want to be the same as the probability mass when you integrate from A minus C to B minus C for any constant C. All right? So this is what it means. You want it to be translation invariant. You want this to be equal to that, okay, for any C. So if you play with integrals and change of variables in the integration, that it comes out that for any C, you need to satisfy that the probability of mu has to be equal to the probability of mu minus C, and the only distribution that can do that is basically a distribution that's constant. And a distribution that is constant going from minus infinity to infinity, it's improper because you cannot normalize it. Okay? So this distribution is used very common, let's say, for the mean of a Gaussian, but it's an improper distribution. You cannot normalize it. Is that an issue? It can be an issue, but because we're referring to the mean here, if somehow you do Bayesian inference and you collect at least one data point, the posterior, using this prior, comes to be normalizable. All right, so because you need only one data point to fix the mean. Okay? But the prior itself, it's improper, it's not normalizable. Now, a lot of times in practice, if you don't want to use this, but you want to use sort of if you play with a Gaussian and you want to use a conjugate prior, which is a Gaussian for the mean, what you can do is you can substitute this prior also with this prior, where you take the variance to go to infinity. So what looks like is that this is normalizable, so it's proper. So it looks that is nice. But let me just say that this distribution here has the same deficiencies as the distribution P of mu equal to constant. Okay? And we will see this when we do different examples. So this may be easy sometimes to do algebra with in complicated problems if you play with Gaussians. All right, and it looks proper, but because it's proper, it doesn't save you from weird things, and those weird things include, you remember I mentioned this paradox the other day on the last slide, okay? So this doesn't save you. You can do a scale invariant prior, right? Suppose that, you know, you are looking to change basically the scale in your problem from meters to centimeters, all right? What does it mean to be scale invariant? It's a distribution that has this form. And where sigma is the scale in the problem. And why we call this scale invariant? Because if you use the transformation of coordinates, so if from x you go to x bar, where c is any constant, it comes out that the transformed distribution has the same identical form. Okay? And in common terms, what does it mean actually that this is scale invariant? So let me just tell you what it means. It means if you compute the probability from A to B, it comes out to be the same as the probability from A divided by C to B divided by C for every C. So if you rescale basically your variables, the probability mass is conserved. And it comes out that the only distribution that can satisfy this scale invariance is the distribution that looks like this. And where do we use this? We use this for the variance, or you can think this of the standard deviation as well. P of sigma is equal to 1 over sigma, or equivalently, P of log of sigma is constant. By the way, if P of sigma is 1 over sigma, what's the P of sigma squared? Using the transformation laws. If P of sigma is 1 over sigma, what is P of sigma squared? One over sigma squared, okay? And then the same is actually true for the precision, the inverse of the variance. So, you can write basically the same equation for the precision. All right, if I don't like to use this improper prior, is there any proper prior that on the limit basically gives me 1 over sigma? In this case, actually, you don't have to take any limit. If you take a gamma distribution with parameters 0 and 0, then P of sigma is 1 over sigma, so immediately you get this improper prior. It's improper again because you cannot integrate it. Okay, it's 1 over sigma, but the posterior, if you collect two data, you can fix the scale in your problem, the variance. So with two data, basically the posterior becomes proper and you don't have any issues. So what I want you to remember actually from all of these formulas is the following, right? I want you to remember that for a translation invariant prior, we use it mostly for the mean of a distribution, and it is the common sense answer which says the mean can be anywhere. It's a uniform distribution, all right? So remember this P of mu equal to constant, and when you talk about scale invariant, we're referring mainly to the variance, and the improper prior is 1 over sigma, okay? 1 over sigma. And remember, for P of sigma squared is also 1 over sigma squared, okay? Comes from the transformation laws using this improper prior. All right, so this is basically the same idea here. From where do these priors actually come in a sort of a little bit more fundamental mathematical way? All of these priors are actually going with the name of Jeffreys non-informative priors. Okay, what is Jeffreys non-informative priors? This is the definition. The first thing you need to do is define the Fisher information, which is minus the expectation with respect to the distribution of the data of the second derivative of the log likelihood. If theta is a vector, right, it will come to be a matrix. So pi of theta is basically proportional to the determinant of this matrix to the power of 1/2. So this is what Jeffreys non-informative prior is. I'm going to give you examples. By the way, this Fisher information matrix and this sort of modification to other priors, I discussed it before. If you want to enforce the map estimates to parameterize properly with coordinate changes, you had to plug in this determinant 1/2 to this unnormalized posterior. So somewhere we saw this in an earlier slide. But this is what Jeffrey came, all right? There is much mathematics on the motivation of doing this. But can you tell me something you don't really like about this prior, just looking at it? What is there that is like, this is not acceptable? There is something there that should bug you, all right? So this is a model for a prior, and where is that prior coming, looking at this slide? It comes from where? The likelihood. Wait a second, what prior is there? Prior means before you see any data, but this prior depends on the data. No good. Okay? You know what? Statisticians will tell you, look, you know what? If I make this to work, okay, and I violate a principle here and there, it's okay, statistics. Okay, so this violates basically, it violates the concept that we have these, a prior that depends on the data, and then of course, it may violate what's called the likelihood principle. All right, so when you try to calculate estimates of the parameters for two models that basically have the same form of the likelihood, you may get different answers. Okay? All right, so let me say the good things now. The good thing is that the Jeffreys prior satisfies the reparametrization automatically. So if, for example, you change the coordinates and you go from theta to phi, all right, this is the general equation. This is automatically taken care with the Jeffreys priors, because look at this Fisher information matrix. Here you have, let's say, to define the Fisher information matrix for the parameters phi, involves second derivatives with respect to phi, chain rule like this. So if you plug in this outside this expectation, what you get is the Fisher information matrix for theta times this square. So when you take, you remember the priors is the square root of that. All right, so we'll take the square root. Immediately what you see is this reparametrization equation is taken care automatically. So in other ways, when you use this Jeffreys priors, you don't have to worry about changing the coordinates, because this is embedded directly in the form of these priors. A few simple examples. If you have data from a Gaussian and your parameter, the unknown, is the mean theta, so the likelihood looks like this. I suppose you have seen this for the Gaussian, right? I have this all over in the notes. So x bar is the sample mean, so the likelihood can be written in a compact form like that. So this is sort of your sufficient statistics. If you take second derivatives of this with respect to the parameters theta, the answer comes to be minus n over sigma squared. And you notice there is no dependence on the data here. So when you take expectation, it makes no difference. So the Jeffreys prior is the uniform prior, which is exactly what we saw with the location invariant non-informative priors before. So basically this location and scale invariant priors are really Jeffreys non-informative priors. That's from where they come. Okay, so pi of theta uniform comes. It's a Jeffreys non-informative prior for the mean. You can do the same thing for the variance. All right, and again, I advise you to look at the calculations. When you look at the slides, I can spend half an hour talking about the slide, but trust me, if I spend half an hour on the slide, it's not going to be very helpful, because it will be an esoteric sort of calculation that you should do it on your own. Okay, the idea here is there is a little bit of algebra that we may spend 10 minutes, but it's not going to be helpful algebra, because it's boring algebra. So we have data from a Gaussian. The variance is the unknown here. We take the mean to be the constant. So the likelihood looks like this. Again, x bar is the sample mean, theta is the variance. So you take second derivatives with respect to theta, looks like that. And then what you have to do is you have to take expectations with respect to the distribution of the data. So everywhere you see an x, you have to take expectations. So can you tell me actually how this expectation gave me n over theta squared? What happened here? How from this I went to that? What is the expectation of this? Remember, the actual data come from a distribution with mean mu and a variance theta. So when you take the expectation of this, what do you get? You get n times theta, okay? So basically, the Fisher information matrix comes to be n over 2 theta squared. And so the Jeffreys prior is the square root of that. So it's 1 over theta which is exactly what we have seen before. Okay? So pi for the variance, sigma squared is 1 over sigma squared. So this prior favors small variances. And again, we derive it here for pi of sigma squared. If you use transformation and you compute pi of sigma, it will also come 1 over sigma, but usually we play with sigma squared or the precision lambda, which is 1 over sigma squared. There is a pathology with this Fisher information matrix and this Jeffreys non-informative prior. I'm going to describe it, so you don't have to know all the calculations. So actually, I'm going to bypass the slide, and I'm going to come back to it. So here's the pathology. Imagine we try to compute the Jeffrey prior simultaneously for mu and sigma. All right? So let me ask the following first. If you take that mu and sigma to be independent, what is Jeffrey's priors for mu and sigma? So if we take mu and sigma to be independent, what is Jeffrey's prior for the mu and sigma together? Will be, because we take to be independent, will be the Jeffrey's prior for mu, which is how much? It's uniform 1. And what is the Jeffrey's priors for sigma? 1 over sigma. If, however, you take them jointly together and you do your calculation, it comes out that the joint distribution for mu and sigma, notice I don't have sigma squared here, right? Just mu and sigma. It comes out that the joint distribution is 1 over sigma squared. No good. All right? So again, separately, the prior is 1 over sigma. When you calculate it together, you get 1 over sigma squared. And again, I emphasize, you get 1 over sigma squared. This is the standard deviation, it's not the variance. Okay? So obviously, you will get wrong results if you do it for the variance as well. And I mentioned to you that the proper beta prior is not, the non-informative prior for the beta distribution is not beta 1, 1 that you read in the books. It's really beta with parameters 1/2 and 1/2. How do you do this? Well, you take a binomial likelihood, you compute the Fisher information matrix, you take expectations and square roots eventually, and it comes out that the distribution is the beta 1/2, 1/2. This is sort of a little secret that you will only see in a few books written explicitly, and generalizes to the Dirichlet distribution. So if you have a Dirichlet distribution with k indices, the uniform prior is not 1, 1, 1, 1, or 1 over k, where k is the number of states, is 1/2, 1/2, 1/2, right? The proper, proper mathematically proper Jeffrey's non-informative prior for the beta and the Dirichlet distribution basically have 1/2, 1/2 here. So you may want to go back and revisit that problem with the N1 regularization to see what happens when actually you repeat those calculations and your prior has not 1, 1 parameters, but 1/2, 1/2. All right, and let me know. We only have a few minutes, okay? So the idea is whatever prior you use, especially if you have limited data, you need to be sure that your calculations are not very sensitive to that prior. And what I mean with that, so here is a calculation. We do two calculations for two posterior distributions. Let me see what we take as unknown here. So I suppose the unknown here, all right? The unknown here is the mean of a Gaussian. So what we take a flat prior, so it's uniform, everywhere the same, and then we take something, we take a conjugate prior that looks like this, okay? And you notice the difference of the posterior that you get. I don't know, does it say how many data points you use here? Okay? Somehow what you need to be careful is, right, if you have any prior, do some sort of sensitivity analysis and see, does it really affect significantly the results? And if you see lack of robustness, you have to look for something else. In some sense, you need to look at the prior as a way to regularize your solution, not really to tell you something different from what the data tell you, okay? And if you want to really sort of address this problem, then you have to use what's called robust priors, okay? And so what we will do on tomorrow, maybe I will start directly on this hierarchical Bayesian analysis so we can discuss the problem that you have in your homework that in essence incorporates practically everything that we have covered in the course up to now, okay? And there are 3 examples in the slides, so we will do at least 2 of those examples, so you may want to take a look, okay? So, so I'm going to abandon you there. Okay, all right. I explained to you, right? You can transfer anything you want to, but it will not matter if there is a problem. Okay. All right, so I sign everything. Bring them, actually, let me have some minutes, right? Bring them like after 3 o'clock. Okay, I'll be here at 6.